So this is the third lecture of week number 10, and in the previous lecture we had gone through two problems related to the air conditioning part of this course, and we will go through another problem in which I will go through the solution procedure, and then you can apply that procedure to the problem and obtain the desired results. So I will put up the question on the screen and then go through the solution procedure. The problem relates to a terminal reheat system for two zones in which information pertaining to the outside design conditions, the respective zone design conditions, and some other information is provided, and based on that information we are asked to find out the supply air mass flow rate for the two zones and the reheat capacity for each of the zones and the cooling coil capacity. So remember, in a terminal reheat system you have a reheat boxes or reheat terminals before each of the zones, and according to the requirements of the zone you will provide the reheat for each of the zones that you are conditioning. We have discussed this type of a system earlier, and I had also given you the psychrometric diagram of this cycle, and that is what we will start with. We will go back to that psychrometric diagram in which the terminal reheat cycle is sketched, and then try to see how we will proceed with the solution. You can see the schematic the cyclic representation on the psychrometric diagram. We have the two zones, zone A and B, for which if you look at this point 6 or 7 or 1, they are all the same states, and when you refer to the schematic diagram of this arrangement, which you can refer to from the earlier lectures, you will see that this is the state at which the conditioned air leaves the cooling coil, and then that air will be reheated as per requirement of each of the zones. So for zone A you will reheat it from state 6 to state 1A, and similarly for zone B you will reheat it from state 6 to state 1B. Then that air will be supplied to the zone where it will balance the heat gain, both sensible and latent. You can see the load ratio line for zone B, and there is a load ratio line for zone A. The same two lines are shown on the protector over here, so these lines would be parallel, and we can try to see that these are actually the lines that we are looking at. For example, if I look at this line, that has the same slope as the slope for zone A, and the other line then should be the line which shows the slope or the direction of the process for zone B. And when the air exits the two zones, that air is combined into a single stream, which is shown by the state 2 or 3. Then that stream is mixed with the outside air after part of it is exhausted, and the rest is recirculated and mixed with the outside air, which is at state 4. Then the mixed air conditioned is at state 5, and then that air goes to the cooling coil, so there is the cooling and dehumidification process shown over here. And as I had said earlier, when we solve problems of this sort, what we should try to do is to first obtain all the state points, and then we can complete the cycle on the psychrometric chart. And while we do that, we might obtain some intermediate results, and when we have completed the cycle, any other remaining results can be obtained from there. So let's start with the problem that we have been given and see which states can we locate and then how to proceed onwards. So we are told that the air, when it leaves the cooling coil, is saturated and it is at a dry bulb temperature of 15 degrees C. So because it is saturated, only the dry bulb temperature is sufficient. That is, you will mark state 6 on the saturation line corresponding to a dry bulb temperature of 15 degrees C. In this schematic diagram of in this sketch, it is not shown on the saturation line, but when you actually solve this problem, it will lie on the saturation line. So we might have state 6 somewhere over here. Let's say it is over here, and this is on the saturation line. I'll just try to extend it slightly. So this is, and this will be at 15 degrees C. So we've got state 6, 7 or 1, they are all the same. Then we can locate state 2A, because the design conditions for zone A are given as 15 degrees C dry bulb temperature and 40% relative humidity, and we can locate state 2A. The sensible and latent loads for zone A are also given, so we can easily find out the sensible heat factor for zone A, which is the sensible load divided by the total load, and that comes out to be 0.80. So we know that state 1A will lie on a straight line drawn from state 6, because from 6 to 1A and from 6 to 1B we have the reheating, and that is just a sensible heating process. So what you will do is that from state 6 you will draw a line of constant humidity ratio, and both states 1A and 1B, they must lie on this line. We have now located state 2A, and I'll just mark it off that we have got state 2A. Let's give it a different color. And also we have located state 6 or 7 or 1, so I will also identify that 6, 7 or 1, it's on the saturation line, so we will assume this is on the saturation line. So we've got these two states. Then, because we know the sensible heat factor for zone A, we can use the protector, and on the protector you will draw the line corresponding to a sensible heat factor of 0.8. I will just show it arbitrarily over here because this is not according to the data, this is just a general representation. So let's say this is 0.8, and what we have to do is we will have to draw a line parallel to this line from state 2A, and when you do that, it will intersect this line that we have drawn from state 6 at 1A, and that will establish state 1A on the psychrometric chart. So we can say that we have also located state 1A Then we can also find out the dry bulb temperature at this state. All you have to do is to just draw a line from over here, a vertical line, and that will give you the dry bulb temperature at state 1A, and I leave it to you to find out that value. We can now repeat the same procedure to locate state 2B and then find out the dry bulb temperature at state 1A. So we will locate state 2B because the design conditions are given. Then we will find out the sensible heat factor, and again we will locate state 1B on the constant humidity ratio line, and that is the next step. You can see that on the psychrometric sketch I have shown these points that we have located. We started with state 6, located state 2A, used the sensible heat factor, located state 1A, found out the dry bulb temperature at state 1A. Then similarly you can see that we can locate state 2B because we are given the dry bulb temperature and the relative humidity. Then the sensible heat factor is also worked out from the sensible and latent loads. Once we have got those, we will use the protector and then locate state 1B, and at that state we can then find out the dry bulb temperature. So that is the way we can locate states 1A and 1B. We can also find out the mass flow rates for the two zones. Remember, the mass flow rate that is supplied to zone A will be the mass flow rate at state 1A, and similarly the mass flow rate that is supplied to zone B will be the mass flow rate at state 1B. And that is quite straightforward because we are given the sensible load for that zone. We can then easily find out the mass flow rate because we know that the rate of energy transfer is equal to the mass flow rate into the specific heat into the temperature difference for sensible heating or sensible cooling, and we can use that basic relationship to find out the desired mass flow rates to the two zones. Let's proceed further with that. Okay. So the sensible load for zone A is given to us. Mass flow rate for zone A is to be worked out. Specific heat for air will take the standard value of 1 kilojoule per kilogram Kelvin. The temperature T2A we were given, T1A we have found out, so you will find out the mass flow rate for zone A, and along the same lines you will find out the mass flow rate for zone B, and that is in kilogram dry air per second. And once we know what is the rate of mass flow rate to each of the zones, then we can find out the energy supplied at the reheat terminals. And the equation, because it's sensible heating, equation is the same, that the energy transfer rate is equal to the mass flow rate into the specific heat into the temperature difference. And remember, the air after the cooling coil is at a temperature T1, or you can say T6 or T7, they are all the same, and that air is heated by the individual reheat terminals. So it will be heated to a temperature T1A for zone A, and it will be heated to temperature T1B for zone B accordingly. So the reheat energy requirement for zone A is equal to the mass flow rate for zone A into the specific heat into T1A minus T1, and once you put in the numerical values you will get the desired energy transfer rate in kilowatts. And similarly the reheat for zone B can be found out because we know the mass flow rates and the temperatures are also known to us now. If you refer to the psychrometric diagram, you can see that we now have three states which are yet to be located, that is state 2, state 4 and state 5, and they can also be found out by applying energy and mass balances. So because state 2 or state 3 is obtained by the mixing of the two states, that is state 2a and 2b, we can perform an energy balance, and that will give us state 2. State 4 is the condition of the outside air, and that is given to us, so we can easily locate state 4. That leaves us with state 5, and remember state 5 is again a diabatic mixing of two states, that is state 2 and state 4, and again we can apply the energy and mass balances to locate state 5. You are given in the, if you read the problem, the amount of the recirculated air and the proportion of the outside air, so that information will be utilized, and of course we will need the enthalpies when we perform energy balance, and that will help us locate state 5, and that sort of an exercise we have done earlier as well in other problems. So you should be familiar with the use of that process in locating states 2 and state 5. And once we have got all these states, the only thing that remains to be found out is the cooling coil load, and for the cooling coil load we have the equation that we had used earlier as well. Of course the symbols are different this time, but the basic equations remains the same. That is, across the cooling coil the enthalpy difference is from state 5 to state 6, and the mass flow rate is the total mass flow rate that we have at state 5, which is the sum of the mass flow rate at state 4 and state 2. Or we can say it is the sum of the mass flow rates of the two zones, m dot 1a plus m dot 1b. And then of course in this equation we have an additional term. Remember, this represents the energy that is carried away by the condensed fluid, and for that we need the humidity ratios at states 5 and 6, and we are assuming that the condensate leaves the cooling coil at the saturation condition of state 6. So you can find out the value of HF at 15 degrees C from the table, and then you will get the capacity of the cooling coil. So that is the procedure, and you can follow this procedure and obtain the values that are required in the problem. So that concludes the numericals that we were going through at the end of the course, and I will now go through a few videos to further show you some of the components that we have talked about. If you recall, in a central air conditioning system we have the plant room in which you have the refrigeration system, you have the pumps, you have the hot water boiler, etc. And you frequently come across a term called the chiller. What a chiller is and how does it look like? Okay. Now that is something that I will show you by using a video, and actually a chiller is the entire refrigeration unit. That means it contains the condenser, the expansion device, the evaporator, and the compressor. And we will look at a video in which you will see the view of a typical chiller unit. Okay. So let's go through that video, and then we will move on to two more videos along the same lines. Now if you look at this figure, this is a typical chiller, and over here we have the compressor. So this is actually the compressor if you focus on the cursor, and this is the motor which is driving the compressor. And remember, the inlet to the compressor is from the evaporator. So this vessel over here is a shell and tube heat exchanger, which is a evaporator in this particular application. And then from the compressor, the compressed vapor will go into the condenser, so that other vessel, which also is a shell and tube heat exchanger, would be the condenser, and in between there will be the expansion valve and other valves for various purposes, for safety and other requirements. So we have a view of the chiller, and you will see the other side as well. So over here we will have the expansion valves, you will have the refrigerant receiver, and some other safety valves also. You can see this is the inlet to the compressor, and this is the outlet from the compressor, from which the superheated vapor at high pressure goes into the condenser. Now these connections over here are for water. We have a water cooled condenser, so you will have the water coming into the condenser, and it will be then sent to the cooling tower. So there are two connections for the water, one inlet, the other will be the outlet. And similarly, from the evaporator we will have chilled water going to the air handling unit. So you will have the chilled water coming in, it will be flowing through the pipes, and then the refrigerant will be evaporating on the shell side. The chilled water will then be pumped back to the air handling unit for the cooling of the air over there. Yes, you can see the interconnecting piping, which will allow the condensed refrigerant vapor to be passed to the expansion device, and then it will go back to the evaporator. The next video will show you how the expansion valves are used in a commercial vapor compression system chiller. So let's go through this video as well.
Hey there guys, Paul here from theengineeringmindset.com. In this video we are going to be looking at the thermal expansion valve on a chiller. Now the expansion valve is located between the condenser and the evaporator, and in this version it is located just here. So in this video we're going to look at the three most common types of expansion valves in typical modern chillers, that being the pilot operated thermal expansion valve, the thermal expansion valve, and also the electronics expansion valve. But first, what does an expansion valve do? Well, the expansion valve controls how much refrigerant flows between the condenser and the evaporator. The valve responds to the suction line superheat which is entering the compressor. This is the suction line here going into the compressor. and it will vary the amount of refrigerant flowing into this to suit the change in the cooling load. So the evaporator needs to have a certain amount of liquid refrigerant in it for the heat exchange to occur, or for sufficient heat exchange to occur. If there's a lot of superheat coming from the evaporator, then that means there's a lot of vapor in there, and that means there is not enough liquid refrigerant in the evaporator, so more needs to enter. So the expansion valve is keeping that balance between the right amount of liquid refrigerant and the right amount of superheat. You only want vapor entering into the compressor. If liquid gets in there, too much liquid, it will break the compressor. The compressor does not like liquid entering it. So keeping the right amount of superheat entering the compressor keeps your compressor and your chiller healthy, and also allows it to run in a much more efficient manner. So the first expansion valve we're going to look at is the pilot operated thermal expansion valve. In the real world, the pilot operated thermal expansion valve will look something like this. Here we've got the pilot expansion valve located just here, and over here we've got the main thermal expansion valve. Now the refrigerant will flow from the condenser. This is the condenser here, and the refrigerant will flow into this. This is a king valve, just so you can isolate it and you can lock that off. So it will flow through this valve, up through this tube and into the base of the main expansion valve, and then up into the evaporator. To control this flow, we've got the pilot operated thermal expansion valve, and that is also fed refrigerant from the base of the condenser. This flows through this tube here into the valve. The valve decides if it can flow in or not. That flows through into the base of this, the main expansion valve, and this flow is what controls the main valve. Attached to the pilot expansion valve is this capillary tube. This rides up and attaches up into a thermal bulb, which is placed on the suction line of the compressor. So just to give you a side view there of how it's all connected. So we've got the pilot valve located down here with the connection going to the condenser, and that flowing through into the base of the main expansion valve. We've also got the capillary tube, which rides up here into the thermal bulb, which is attached to the suction line just before the compressor. And then the main refrigerant flow will pass through here, through this pipe, into the main valve. This expansion valve decides if it's allowed to pass or not, and if it is, then the refrigerant will flow into the evaporator. So the thermal bulb will be located on the on the suction line, and it looks a bit like this, with the capillary tube running along here. Now this thermal bulb is filled with a refrigerant. When the superheat increases, this starts to cause a heat transfer across into the bulb. Usually this is covered with an insulation. You can see here I've just cut the insulation open so you can see it. It's important I replaced it back afterwards. But the superheat will transfer its thermal energy into this bulb. The bulb is filled with the refrigerant, and that refrigerant starts to boil and expand. As that expands, it pushes refrigerant out through the capillary tube, and that causes a pressure increase in the capillary tube, and that pressure pushes all the way along the capillary tube, all the way down through it and into the top of the pilot valve. So that pressure is pushing down onto the top of the valve, and with that you can now control the valve depending on the level of superheat. So we can look at a section view here. So we've got the condenser on the side, the evaporator located above. We've got the capillary tube riding up and connecting onto the suction line. Down the bottom we've got the pilot expansion valve. This is connected through with a liquid line going to the main expansion valve. Inside there is a piston body and spring. This piston body and spring is what will control and allow this refrigerant to flow through into the evaporator. So as the pressure increases in the capillary tube and it starts to build up and push down on this valve, you can see inside the valve there is a diaphragm which is connected to some push rods and then onto this valve head, which is also spring loaded. There are a few variants of this design, but this is probably the simplest and one of the most common used. So as that pressure increases and starts to push down on that diaphragm pushes against the piston rods, and these rods push the valve head down, and that causes a slight gap to form there, and this allows refrigerant to start flowing out. So the refrigerant is starting to flow from the condenser through here and into the pilot valve, and then that is going to start to flow through into the liquid line. As that refrigerant starts to fill the liquid line, it starts to build up some pressure and starts pushing against this piston housing here. That pressure is going to lift the piston off its seat, and that's going to allow the main refrigerant in the condenser to start to flow through this valve. When the bulb detects the maximum allowable superheat, it's at full pressure now. The refrigerant inside is fully expanded, and that's pushed down the pin rods inside the expansion valve all the way down to the maximum amount of refrigerant from the condenser is now flowing into this through the line, and has pushed the piston body completely off its seat, and that is allowing the maximum amount of refrigerant to flow into the evaporator from the condenser. The next expansion valve we're going to look at is the thermal expansion valve. In the real world, the thermal expansion valve looks something just like this. So this one is actually on an air-cooled chiller, but it's still got the flow of refrigerant coming through and then going off into the evaporator, and you've also got the equalizer valve coming through there, and attached to the top of the thermal valve is the capillary tube, which goes off and measures the superheat. Now these type of valves are usually found on smaller chillers. As they start to get larger, that's when they move over to the pilot operated valve to give much better control. So the thermal expansion valve is very similar to the pilot operated one, except that it hasn't got the main expansion valve there. The thermal expansion valve is the main valve in this type. So again, we've got the capillary tube rising up and connecting onto the suction line to measure the superheat, and we've got the refrigerant in the condenser, which will flow through, is being held back currently by the valve head, and once released, that will flow then off into the evaporator. So the pressure is starting to build in the capillary tube due to the superheat transferring its thermal energy over into the thermal bulb and expanding that refrigerant. That pressure increasing and pushing down the diaphragm, which pushes down on the pins and starts to knock the valve body off of its position, allowing some refrigerant to start flowing from the condenser and into the main valve. That refrigerant then starts to flow and goes off into the evaporator, and finally, once the maximum amount of allowable superheat is there, the valve body opens fully, allowing the maximum amount of refrigerant to flow from the condenser and through into the evaporator. So this type of expansion valve is exactly how you would find in a kind of a household air conditioning unit, but the valve is just a slightly bigger version, obviously to handle the load of the cooling load, which it needs to for the size of the chiller. The third expansion valve we're going to look at in this video is the electronic expansion valve. Now in the real world, the electronic expansion valve will look like this. You can see it highlighted in the circle here. Now this type of expansion valve gives the best performance, and that's because the valve here actually uses a stepper motor in the body, and that precisely controls the positioning of the valve body inside, allowing a very accurate and precise flow of refrigerant. So the electronic expansion valve, I've just illustrated that here. So we've got the main shaft connected to the valve head inside the body there. Then behind that we've got the stepper motor, and that is connected to a controller. The controller measures the temperature and pressure from the evaporator outlet, and this allows the superheat to be calculated and that value to be determined. The controller decides is there enough superheat or not, and then sends a signal to the stepper motor to very precisely control this shaft in the valve head to move that back to allow and adjust the refrigerant flow rate. So that refrigerant in the condenser flows along the liquid line into the base of the motor, or the valve, sorry. The controller is sensing that more refrigerant is required in the evaporator, so that sends the signal to the stepper motor just to pull that valve head back slightly and allow some refrigerant to start flowing. That refrigerant then flows off into the evaporator, and then at the maximum demands, the stepper motor has been moved and rotated the complete rotation, and that has pulled the valve body back, allowing the maximum amount of condenser refrigerant liquid here to flow off into the evaporator, and it will modulate back, changing the position of that motor and the shaft position to control and very accurately control the amount of refrigerant flowing into the evaporator. As with all the expansion valves featured in this video, you can see here the performance. So the expansion valve is located here, just here on the chart here. So that is going from 0.3 to 0.4, and that means the refrigerant is going to change from a high pressure to a low pressure, from a medium temperature to a lower temperature, and it's going to go from a saturated liquid to a liquid vapor mix. And you can see this on the chart. So if you're looking at the pressures axis, you can see there's a change in pressure, a decrease in pressure. There is a decrease in temperature. There is also an increase in entropy, but a consistent enthalpy. Okay, that's the end of this video. Thank you very much for watching.
What we had looked at was earlier the vapor absorption chiller, but we have also studied another type of refrigeration system, which is the we had looked at the vapor compression chiller, and we have also studied the vapor absorption system. So the figure that in front of you is a photograph of a typical vapor absorption chiller, and again it contains all those basic components that you will have studied. That is, you have a condenser, you have the evaporator, then you have the absorber, and you have the generator. And of course the actual system is more complex in the sense that it requires a number of control mechanisms, safety features, which are all incorporated into a single unit, and these generally tend to be bulkier than the typical vapor compression chiller, and they tend to be even more expensive. But as you had studied earlier, over time, because they require a very small amount of energy, or they require energy at a very low cost, which is available, for example, from generators, that is the waste heat, or from other processes which are generating, let's say, process steam, the initial high cost of investment is recovered by the low operating costs. Okay, I will now conclude by showing you another video, and this is a video of a typical plant room, and you will see the various components and the systems that are present in a typical plant room.
Well, hello and welcome to another Corporate Facilities Group informational video. I am Paul Housleben, and I am the Vice President of Operations for Corporate Facilities Group. We're based in Atlanta, Georgia, and we are a leading provider of facility management, property management, and maintenance services, as well as technical consulting. And today, we'd like to walk you through some basic chiller plant operations of a fairly large office building. We cover the nation, even though we're based in Atlanta, Georgia. I am in Virginia today at a building that was renovated about 4 years ago from single tenant use to multi-tenant. And during that renovation period, we also totally rebuilt and updated the chiller plant. This is just basic information on how a chiller plant operates. This, of course, is the cooling systems for the building. And this is an office building, so this is comfort cooling. We have a small data center operation here, but it's handled by independent little package units, not a large data center operation. Sorry for all the noise here, but chiller plants tend to be quite noisy. So we'll run you through real quick here, basic chiller plant operation. And this building is about a little over 100,000 square foot. We'll call it 310,000 square foot. So we have two 400-ton chillers that I'm looking at right now. These were updated. The original chillers used old-fashioned refrigerant, R11 refrigerant, and they were removed in a renovation and replaced with these high-tech Dakin McQuay chillers. If you look closely on the top of the chiller there, and I will do my best to kind of zoom in here a little bit, and you will see that these have high-tech motors on the top that actually use no oil. These motors run in a suspended animation, so they have no real friction, and they save you a ton of money on electrical over the old-fashioned chillers. Both of these chillers are not running. It's a very cold morning here. I'm going to walk over to this one, and you can see it has a really nice screen on there that gives you some eye candy of pretty much what's happening with the machine as far as pressures go and temperatures. Here you can see the little motor nomenclature on top. But we're going to look at the chiller and tell you how it works. Now, basic physics and refrigeration principles come into effect. If you buy a carton of milk at the grocery store and you put it in your refrigerator, the refrigerator actually removes the heat from that milk, and therefore it makes it cold. Basic physics with hot and cold principles. So a chiller works on the same principle. It makes cold water, which is circulated through the building, attracts the heat, picks the heat back up, and removes the heat through what we call a condensing loop. So we have two sides of the chiller. We have the chill water side, which has the insulation on it, and we have the condensing side, which is non-insulated because it's warm. And pretty much what we do is we make cold water with the compressors and the refrigerant. You can see the chill water pipes. We'll follow them, and they come across top of the chiller plant, and they go to a series of pumps. These pumps pump the chill water up and down through the building to a series of air handler coils staged throughout the facility, and that has a fan behind it which blows the cool air into distribution boxes in the office space. And that's an oversimplification, but that's pretty much how it works. Now, as the heat is picked up in the loop and it comes back to the chiller machine, the heat is then put into the condensing side and rejected out through a system called a cooling tower. And we'll take a look at the cooling tower. Now, this is a water side condensing chiller plant, and they require a lot of maintenance. As you can see, this one is pretty much kept immaculate. Guys do a great job here. But you do have to attend to your chiller plant pretty much 3 or 4 times a day. So here comes the warm water in the condensing loop. It goes to these pumps, and then it leads to outside where there's a cooling tower sitting on the outside. And the cooling tower is a large reservoir, and it has fans at the top of it, and the fans reject the heat into the atmosphere. We'll take a walk out there. It's kind of dark and cold today, but we'll do the best we can. This is a sump heater, and what this does is it keeps the basin of the cooling tower from freezing solid. It does get quite cool here in this part of Virginia. It gets awful hot and humid in the summer too. So there you have a heater. It's an electric heater which tries to prevent it from freezing solid. There's also heaters in the bottom of the sump of the cooling tower. Now, this building also has a nice feature with what's called an economizer. and that's what we're looking at now, or a heat exchanger. And what this piece of equipment does, through some sophisticated automation, which is located in the building in the chief building engineer's office, it watches a condition called enthalpy. And when it decides that the outside temperatures and the water in the cooling tower has now become so cold that it can utilize that water for free cooling, it shuts the machines off, chiller machines, captures that water, circulates it through this machine, which is basically just a bunch of copper plates, and migrates the cold water from the outside to the warm building chilled water, which comes in there, and therefore through principles of physics, it takes the cold water and makes free chilled water, courtesy of nature. So that's a pretty cool operation. There's a series of valves up there. If this water gets too warm, what it does is it'll shut these valves off automatically, and then once more just turn your chiller back on to have the mechanical cooling. So pretty cool little system. Like I said, it gets cold here in Virginia, and if we have a good week or two of real cold temperatures, this water will stay cold for a long time, and the owner will reap a lot of benefits here, because this will save him a bundle of electricity in running these machines. Even though these machines are quite economical, you can imagine, you know what your electric bills are at home. If you run these machines for a long time, it's going to cost some money. When we did the retrofit here, we preferred to keep the old-fashioned pneumatic actuators, which are air valves, or air actuators that operate mechanical valves. They're very, very reliable. They've been here for years. Every couple of years, the crew here will replace the diaphragms or do a little maintenance repair on them, but for the most part, they are very trouble-free. Sometimes the electric valves can be a hassle. So we kept the pneumatics. There was nothing wrong with them, and saved a bundle of money on a retrofit to new valves. So with the air valves, we have to make air. So we have a large air compressor here, which makes air for the chiller plant. As you can see, that is an old air compressor, but it's once more kept in immaculate condition by this crew here. To keep the air nice and dry, an enemy of pneumatics is moisture, so we have an air dryer, which is basically a refrigeration unit that dries the air leaving the compressor. Also removes some oil. Because these are new chillers, they do use a new refrigerant, which is not a happy chemical, and it is toxic, as opposed to the R11 refrigerant, which was an ozone killer, but it was not deadly. So if we have a catastrophic failure here and a refrigerant leak, we do have a sophisticated detector here, which is constantly sampling the air for any issues. It will lock down this chiller plant so that no one can enter. And over here, it will turn an emergency fan on, which will evacuate the air up through and out to the atmosphere. It will also take in a bundle of fresh air through this system here, and of course replenish the bad stuff with fresh air.
So that concludes this final lecture of this course in refrigeration and air conditioning. Thank you.